You know that feeling when you hear a car with an inline-6 engine and it just purrs? It's incredibly smooth. But then you hear some V6 engines and they can be, well, a little rough around the edges. That's not just in your head, it's physics. And today, we're going to get our hands dirty and really dive into the super complex engineering challenge of how you tame all those wild forces inside a V6 engine.
So, here's the plan. We'll start with the basic problem, then look at how engineers use geometry and some clever mechanics to solve it. After that, we'll get into the math that actually proves it all works. And finally, we'll see a head-to-head comparison and figure out why any of this really matters. Let's get into it.
All right, so what's the big deal with the V6? Why is it so inherently shaky? It really all comes down to its design. See, a V6 is a compromise. It's trading that perfect natural balance for a compact shape that can squeeze into pretty much any engine bay. An inline-6, on the other hand, is just naturally balanced. You've got 6 pistons all in a row, moving in pairs that perfectly cancel out each other's vibrations. It's beautiful. A V6, though, it's basically 2 3-cylinder engines stuck together, and a 3-cylinder engine is just not balanced. This creates what we call primary imbalances, that's the big up and down shaking, and secondary imbalances, which are these higher frequency vibrations that engineers have to work really hard to get rid of. And this quote from Slash Gear really hits the nail on the head. That odd number of cylinders, 3 on each side, is the root of the whole problem. The forces just don't have a natural partner to cancel out against, and that creates this rocking motion that has to be tackled with some seriously smart engineering. So, the first tool in an engineer's toolbox for fighting this imbalance is geometry. More specifically, it's the angle between the 2 banks of cylinders. We call this the V-angle.
Let me just throw a question out there to you. If you could design a V6 with any angle you wanted, what angle would you pick to get perfect natural balance?
The magic number is 120 degrees. At that angle, the engine's firing intervals are perfectly even, and that gives you super smooth power delivery and way less vibration. So, what's the catch? Well, a 120-degree engine is incredibly wide. I mean, it's just not practical for most cars. So engineers have to compromise, usually with more compact 60 or 90-degree designs. But as soon as they do that, they introduce a new problem: uneven firing intervals.
Okay, so if the geometry of the engine block itself creates this uneven firing, the next solution has to be mechanical. And that takes us deep into the heart of the engine, to the crankshaft. Now, the old-school traditional design is called a common pin crankshaft. It's simple, it's strong, it's cheap to make. But if you use it in a 90-degree V6, you get this really weird firing pattern. It fires, waits 150 degrees, fires again, waits 90, then 150, then 90. You can imagine how that feels. It creates a rough idle and a lumpy torque delivery. Not exactly ideal. And this is where things get really clever. The solution is the split-pin crankshaft. This design literally splits that shared crank pin into 2 separate sections that are offset from each other. It's a brilliant little trick that lets engineers correct for those not-so-perfect V-angles, and it gets them those perfectly even 120-degree firing intervals. The result? A much, much smoother engine.
So, we've talked about the concepts. But hey, we're engineers, right? The real proof is always in the math. So let's take a look at the actual relationships that control all these forces. Don't worry, we're not going to be solving a bunch of differential equations, but we are going to use them to see exactly why these design choices make such a huge difference.
Okay, this diagram is our Rosetta Stone. It defines our 2 most important variables. First, there's gamma. That's the V angle between the cylinder banks. And then there's delta. That's the split pin offset angle we were just talking about. These 2 angles right here, they're the key to unlocking the engine's balance.
And here it is. It all comes down to this one simple, elegant rule. To get that perfectly smooth, even firing, the split pin offset you need, delta, is just the absolute difference between 120 degrees and your V-angle, gamma. It's that simple. So for a 60-degree V6, you need a 60-degree offset. For a 90-degree V6, you need a 30-degree offset. It's so simple, but so powerful. So when you plug that simple rule into all the complex physics, it boils down to this. These 2 equations here describe the moment, which is basically just the twisting or rocking force, in the horizontal, or X, and vertical, or Y directions. You can think of these as the mathematical fingerprint of the engine's vibration. This is our model, and now we can use it to compare different engine designs. All right, we've got the theory, we've got the math, now it's time for the showdown. We're going to use our model to plot out the forces in a 60-degree and a 90-degree split-pin V6 and see which one really comes out on top.
And wow,
The results are really striking. Take a look at the left for the 60-degree engine. See that solid green line, M prime? It's a constant value. It's a flat line. This is huge because a constant force is incredibly easy to balance out perfectly with just a simple counterweight. Now look at the right. The 90-degree engine's moment is all over the place. It's fluctuating. It's certainly better than nothing, but it's nowhere near as clean.
So what does this graph tell us? Well, it shows how big the counterweight needs to be to get the best possible balance for any V-angle. Now for our split pin design, that's the blue line. And check this out, the required counterweight actually gets smaller as the V-angle gets smaller. That's a massive advantage, because it means a lighter crankshaft, which means a more responsive and efficient engine. And here it is, the bottom line. This plot shows how much shaken is left over after you've added the perfect counterweights. So here's the key takeaway. For any V-angle below about 82 degrees, the split pin design, that blue line, is way better balanced. But above that point, and specifically right at 90 degrees, the simpler common pin design actually has a small advantage when it comes to that leftover vibration.
So we've been pretty deep in the weeds with theory and graphs and data, but why does this math really matter? I promise, this is not just some academic exercise. These exact calculations directly influence huge engineering and business decisions.
Let me just put one number on it. 192%. At a 60-degree V-angle, a common pen engine has 192% more of that residual vibration than a split pen engine. That's not just a number on a graph. That's the real-world difference between a rough, shaky engine and a silky smooth luxury car. It's exactly why some car makers could switch their V6 from a 90-degree to a 60-degree design and completely eliminate the balance shaft, a whole complex, expensive part, all because the math we just looked at predicted it would be better.
So let's just wrap this up real quick. Split-pin crankshafts. They're absolutely critical for getting smooth, evenly firing V6s. A 60-degree angle with a split-pin crank is basically the gold standard for balance. Below 82 degrees, split pin is the clear winner. At 90 degrees, the common pin has a tiny edge. But at the end of the day, every engine is this fascinating compromise between perfect balance, how much it costs to make, and, actually fitting it under the hood of a car.
Which kind of leaves us with one final nagging question. If the math so clearly shows that split pin designs are better balanced in most situations, why on earth do we still see so many 90-degree V6 engines out there, sometimes even with the simpler common pin crankshafts? Well, the answer usually comes down to manufacturing. Sometimes it's just a lot cheaper to build a V6 using the same factory tools you're already using for your 90-degree V8s. It's the perfect reminder that, in the real world of engineering, the best solution isn't always just about the physics.